Hi friends, today we are going to study about the stereoisomerism in coordination compounds. So as we know that coordination compounds there are two types of isomerism like structural isomerism and stereoisomerism. So this is the second type. So today I am going to talk about the second type of isomerism in coordination compounds which is stereoisomerism. It is of two types like geometrical isomerism and optical isomerism. Geometrical isomerism is again divided into three types. Similarly, optical isomerism are of three types. The first two types are common for both geometrical and optical. Last type is a little bit different. The first type is MX2L4 in both geometrical and optical, where M represents the central metal atom, X and L are the two different ligands. The ligand X is 2 in number and ligand L is 4 in number. So total 2 plus 4 makes 6 is the coordination number. So the geometry of the molecule is octahedral. And in optical isomerism is also the same type MX2L4 is existing. The second type is MX2LL twice, where X is 2 times and LL represents a diadentate ligand. So one diadentate ligand is of two donor atoms, that 2 into LL type is 2 in number, so total it is 6. This is also octahedral geometry. The same even there in optical isomerism as well. The last type is MX3L3. Here 3 plus 3 makes 6. 6 is the coordination number. So that is also octahedral geometry. And in optical isomerism, it is MLL thrice, where LL represents a diadentate ligand. So one diadentate is having two donor atoms, so that 2 into 3 makes 6 is the coordination number, again octahedral geometry. So today I am going to discuss about the stereoisomerism in all these octahedral complexes. So let's start with the first type. So in first type, we'll discuss about geometrical isomerism first. Here the example which is given as CuCl2NH3 4 times. So I'll show you how to draw the structure of that. As it is octahedral geometry, first you have to draw the skeletal structure. This is the skeletal structure and cobalt is at the center. First you select the ligand which comes as 2 in number in the coordination compound, which is chlorine, Cl2. So chlorine is 2 times. So first you select that ligand and keep it in the adjacent position of the central metal atom. I'm keeping in the right side. And the remaining 4 corners are occupied by the other ligand which is NH3, ammonia. So this is how we can draw the structure in one way which is called a cis isomer. Why? Because in chlorine, here the chlorine, that is the identical atoms came in the same side. At the same time, we can keep chlorine in the opposite side by keeping with the maximum distance up and down. The remaining 4 positions are occupied by ammonia. So if we are doing in this way, here we can say that the identical ligands are in the opposite side. So this comes under trans isomer. So this is how we can draw geometrical isomer of the first example. And the same example, let's look into the optical isomerism as well. For optical isomerism, the condition is the compound should form non-superimposable mirror image. When you take trans and find the mirror image, as chlorine comes in the opposite side like up and down, we will get the same image only. The image will be same, it's not non-superimposable. It will be an identical image, so that it doesn't have optical isomer, or we can say that it is optically inactive. But when you take cis, the first isomer, when you take cis, here chlorine in the right side of the central metal atom, and try to draw the mirror image. This is the mirror, and this is how we can show the mirror, and the chlorine atoms from the right side will be shifting into the left side. So both the isomers are non-identical. Non-identical images are also called a non-superimposable mirror image. Because of that, it is optically active. So cis is optically active. We can say that it is optically active. Why? Because it forms non-superimposable mirror image. And one isomer can be called as dextrorotatory, the other one can be termed as levorotatory, in short D and I. So this is how we can draw geometrical isomerism and optical isomerism for the first type, which is MX2L4. So I hope you understood. Now the second type is MX2LL twice. Let's take the example number 2 for that geometrical isomerism. Let's take the example COCl2 NH3. Instead of NH3, now this time we have to take En twice. Why? Because we have to take a diadentate ligands. Because M, it is X2 LL twice. And for this example, COCl2 En twice, for drawing geometrical isomerism, first always the skeletal geometry, and then cobalt at the center, chlorine in the right side, and there are two En, but we have four corners. So En is a diadentate ligand, so that two corners you connect and write En at the center. This is how we have to represent En. So 2 En needs total 4 corners. This is cis. Why? Because chlorine in the adjacent position. And to keep it in the opposite position, always you keep in the axial positions. So up and down, and the remaining 4 corners. For each 2 corners, 1 En. This is how we can draw the trans isomer. So geometrical isomerism is done. And now if you go for optical isomerism, again for trans, we will get the same image so that it is optically inactive. But for cis, so once more we draw the cis isomer, chlorine in the right side. Again the same structure only I am drawing. And now you take the mirror image. So chlorine and En are changing the position. Chlorine went to the left side so that both the En are coming into the right side. So which is a non-superimposable or a non-identical mirror image. So it's optically active. One is dextro, another one is levo. So this is how we can draw the geometrical and optical isomerism of this type, which is MX2 LL twice. So instead of this LL, here I have taken En as a ligand, but it can be any, like C2 for 2 minus is another didentate ligand. So for any didentate ligand comes, you have to connect 2 corners and write that particular name at the middle. Now last type. Last type for geometrical and optical are different. So first I'll take MX3L3, which comes under geometrical. So number 3, geometrical. Okay. MX3L3, for example, COCl3 NH3. This is a special type. This isomerism will not form cis and trans, instead it forms facial, short form is FAC, and meridional, short form is MER isomer. Why? Because in the previous two example, in these two examples, X2 times are there. Similarly, in the second type also, X2 times are there. One ligand comes as 2 times, that ligand we will select and keep it in the adjacent and opposite position to draw cis and trans. But in type 3, no ligands are coming in 2 times. It is X3 and L3 only. Such cases we cannot select any one ligand and keep it in the adjacent and opposite position, so that this isomerism is not forming cis and trans, instead it forms facial and meridional isomer or FAC or MER isomer. I'll draw how to arrange the molecules, arrange the ligands and central metal atom. Central metal atom, of course, at the center, and there are 6 corners. Let me give the numbers like 1, 2, 3, 4, 5, 6. So what you need to do is you take a face, a particular face. This is an octahedral geometry. Octahedral geometry is having how many faces? First you need to understand that. So there are 6 corners, so that it forms 8 faces, because the middle plane or the central plane is a square planar geometry. From that you will be getting 8 faces, and each face will be looking like a triangle. For example, I'll be joining corner number 1, 2 with the 3. This is how, if I draw, we are getting a triangular plane. And this triangular plane is having 3 corners like 1, 2 and 3. So you need to take any particular plane, any one plane, and those 3 corners are occupied by the same ligand. For example, if it is chlorine you are keeping here, all the 3 positions should be kept with the chlorine and the remaining positions with the NH3. Here you can see NH3 I am arranging with the remaining positions. So instead of 1, 2, 3, if you take 1, 6, 5, that is also a single plane only, same face, same plane having 3 corners. Any particular phase you select and arrange the ligands accordingly. So that is FAC or facial. Okay. Now meridional. To draw meridional isomerism, we know that the central plane is having a square shape and the square is having 4 corners, like 4 vertex like 1, 2, 3 and 4, and we can draw 2 diagonals. So the diagonal positions are 1 and 3. 1 and 3 are the endpoints of a particular diagonal. Similarly, 2, 4 are forming another diagonal position. So what you need to do is you take a particular ligand and keep it in the diagonal position. For example, if I am taking chlorine, you keep it in 1 and 3 position, or else you can keep it in 2 and 4 position. So any 2 similar ligands should come in diagonal position. The third ligand can be anywhere because one ligand is 3 in number. So here I am taking chlorine here and here. The third chlorine can be anywhere. It can be in the equatorial or in the axial plane. Same keeping here, and the remaining positions are occupied by NH3. So the condition for meridional isomerism is it has to form like the meridional position should be occupied with a similar ligand, which is meridional. In short, it is called as mer isomer. Meridional. So this is type 3 geometrical. But type 3 optical, a little bit difference is there in formula. MLL thrice. MLL thrice, for example, COEN thrice. So here again the shape is octahedra only. Why? Because 1 En is 2, 2 into 3 is 6 only. So here you connect cobalt at the center and take 2 corners and write 1 En there. Similarly, the next 2 corners and writing 1 En. The last 2 corners and writing 1 En. This is dextro. And now you take the mirror image. The left and right sides of the species will be different, changing the position like this. So both the isomers are non-identical or non-superimposable mirror image. Because of that, it is optically active. So these are the important types of stereoisomerism. So if you follow this, you will be able to do any of the questions in your textbook. So many questions are there. Please do practice all those. So thank you. I hope you understood.